Hello, thank you for joining us here. I'm Atefeh, and today with Jialin, we'll be talking about our work, Nemotron-CORTEXA. We're from the Applied Deep Learning Research Group at Nvidia, and this is a joint work with Mingji Liu, Rajarshi Roy, Chankyu Lee, Jonathan Raymond, and Brian Catanzaro. So the previous talk gave a very nice introduction to Suibench, and the whole reason for that is that we've seen that LLMs by now are great at solving self-contained coding problems, but real-world software engineering tasks are more than that. Here, the challenge is that we have to start from understanding an issue description. Then the model has to navigate the repository, understand how each of the components connect, and issue a fix for resolving that issue description. And even after that, it has to generate some tests to make sure that the issue is correctly resolved. Here, the problem is that we are dealing with massive code bases that they have millions of tokens. That's far beyond the context window of LLMs. And even if we fill the context window with as much relevant code as possible, much of that is redundant or even misleading. So here we need a comprehensive system that, I don't know what that is, that is capable of doing reasoning, has access to some external tools, and it can make use of, it can efficiently make use of the computational resources at test time. Nemotron-CORTEXA is our approach for doing that, and it's for enhancing LLM agents for software engineering tasks by improving both the localization accuracy and inducing diversity in the solution generation. Our approach has two main stages, localization and repair. In the localization stage, we start by parsing the repository with a custom embedding model that helps us to retrieve the relevant files to the issue. Then we have a localization agent that parses these the files, and it goes through them to identify the relevant functions or classes, what we call entities. And in the repair stage, we combine different contexts with edit formats to leverage diversity in generating solutions. That's helpful for increasing this resolution rate while keeping costs efficient. And finally, we have a series of filtering steps to pick the final patch. Nemotron-CORTEXA topped the leaderboard in May until Cloud 4 was released. So I mentioned that the main challenge here is scale. The problem is that we cannot fit these repositories into the context window. Our first approach here was to just fill the context window with as much relevant code as we could. So we started with the faulty file. That's the file that was edited with the ground truth solution. And we added as much relevant code as we could to it. Then we gradually reduced the number of extra files to see how it will impact the performance. And finally, we narrowed the context to the faulty entities that are the functions and classes. And interestingly, this improved the resolution rate. When we analyzed the reason for failed solutions, we saw that the main mistake of the LLM is misidentifying the Oracle file or those faulty files. So essentially, by doing the localization first, we have made the problem easier, and it's easier for the LLM to succeed. That's why we have built our approach around better localization. And there are so many approaches we can do this localization. We can do keyword search, but you can imagine that it doesn't have a high accuracy. We can parse the whole repository with LLMs, but that can be an overkill. And there are agentic flows that give some tools to the model that the model can navigate the repo on its own. And it can be very effective, but the pool of actions are too large that we are trying to make it more manageable by combining this agentic flow with a variation of the prompt-based. And so for that, we have started building our embedding model that's specialized from going from code issue descriptions to the faulty locations, the parts that needed to be edited to resolve that. Basically, we start by chunking the repository into 450 tokens, and then we are going to check the similarity of these chunks to the issue description. Instead of using the original issue descriptions, we are using an LLM summary of that because we've seen that a lot of times there can be redundancies in them. So we just extract the key names, error messages, and stack traces. We have trained this embedding model on top of a text embedding model and have added a bunch of code retrieval tasks from issue descriptions to code files or retrieving general coding tasks from text or code queries. And this figure is comparing the recall at K for the BM25 prompt-based approach using the skeleton of the repository and the embedding based approaches. K here is the number of Oracle files for each instance. And we can see that for the previous embedding models, they struggle to perform well with the LLM summaries. That can be because there are some mismatches between the linguistic style of these summaries to the training set of those models. But our embedding model not only has better understanding of code data, it can also perform better because these LLM summaries have reduced some redundancies.
Yeah, so Atefeh just talked about our file localization effort. So the step 2 in the process is what we call entity localization. So file localization narrows the problem onto individual files, but still, for Sweetbench, individual files can be thousands of lines, which is still can be too much context for our models. So the step 2 is to further narrow this down to what we call entity level, right? So kind of think about entity that is a function or a class or a method, which is much more targeted edit location. From the previous slide, we know if we provide more targeted edit location, it makes the task easier for the model to generate the correct patch. So, so kind of the first step to enable this is we build this we call a repository graph, which is a graph representation of a repository, and it contains all the entity and their interaction with each other. So here I'm showing you a very simple example of a file that contains 3 different functions. And the functions, they have this call relationship, right? So then we build this very toy graph with like the file node that contains each of the function as an entity. And also there's, when there's function calls, we have this special edge with the type used to label that as function calling. So kind of the intuition is if you use IDEs in your daily development, you know how useful things like language server protocols, like you can look up definition, you can check out, okay, what's the call hierarchy of a specific function, how useful those features can be. And this is really to enable the same thing for the agent that have the similar access to those tools. So once we build this repository graph, we can build a localization agent using this graph. And as I said, so we built several tools. There's 3 specific tools on this repository graph. Get definition, so that's similar in, like, for example, VS Code or Cursor. You can right-click on entity and get definition that shows the source code for that specific entity. And get incoming dependency and outgoing dependency, that's the call hierarchy part, right? So get outgoing dependency, for example, is for a specific function, which other functions this function uses. So that's, you can get this outgoing dependencies. So once we have this graph and tools built in, then we can initialize this iterative flow for this agent. So we start with the same issue description, and the list of top candidate files we generated from the embedding model. And then we prompt the language model to select a starting list of entities. And then we use the graph to fetch the source code for this list of entity using get definition. After the model has seen all the actual source code for those functions, it can decide what the next tool calls to make. And then along the way, we're going to further fetch more code context for the model to contextualize the bug and the issue description. Right? So during the process, as you can imagine, when we get more and more entities, the context builds up, right? Like kind of that defeats the whole purpose of doing the thing to begin with is want to narrow context. So we have this specific step we call the keep as a special command to filter context. So as the model goes along the way, we actually periodically ask it to filter out irrelevant context to keep the context window manageable. So we can repeat the process a few times, and in the end, once the model is confident that it has identified the location, the bug location, it can end the process and output the actual function and entity that needs editing. So we compare this specific entity localization results with AgentList, which is a very popular open source kind of scaffold for solving sweep-bench issues. And here we can see with these with tools and this localization agent, we can get much higher precision recall at identifying the location for the bug, which is going to be crucial for the next step when we want to generate the patch that fixes bugs. And like we employ a specific technique to scale, like kind of the axis of scaling for compute is we employ this we call agent ensemble. So the flowchart showed you can plug in any model and that instantiate a version of agent. So in our work, we instantiate 4 different agents with 4 different models. And then in the end, we take the simple union of their locations as the location results. And you can see here, I want to draw you specific to the recall column. Compared to each individual model, the ensemble gets much higher recall. So meaning that we identify the correct location being contained in the localization results. And sometimes even the extra entities, they can still provide very useful contextual information to help the model in generating the right code for the next step.
So now that we have the right context that the LLM can understand the repository, we can start issuing the patch. Instead of generating the whole file, we're just using these edit formats. Search replace format is showing the actual content of the code with its replacement, and the edit file format is working very similarly, except that it shows the starting and ending line of the original content. In the beginning, I mentioned that as we narrowed down the context, we saw that the number of past instances increased, and you might assume that the instances being resolved by the entity context are a subset of the file level context, but that's actually not the case. And we've seen that changing the context or edit format will result in different instances being resolved, and they have different strength. So like for these 3 choices that we are showing here, that the strength ranges from 19% to 32%. If we take a union of them, we can resolve 40% of them. Usually, when people want to do test time compute and increase the computational resources during test time, they're going to pick the best context and edit format and start doing temperature sampling. But we've seen that if instead we induce diversity by changing the context and edit format, that can increase the number of past instances faster. Like here, by generating 9 solutions, we can get to the same performance of AgentList that generates 40 solutions. Since now we are generating multiple patches, we have to have a way of selecting between them. And for them, we're using regression and reproduction tests. Regression tests are chosen from the existing unit tests in the repository, and reproduction tests are generated by asking the LLM to generating a test that can both check for if the issue is reproduced and if it is resolved. And after this filtering with these tests, we can use different voting mechanisms, either majority voting or LLM voting for picking the final solution. And just to recap, we have developed a code embedding model that's specialized for mapping issue descriptions to their faulty code locations. We've built an agent on top of that that's going to navigate these files to find the more granular localization for this task. And the reason for that is that we saw that once we figure out where we should issue the fix, it's going to be easier for the model to resolve it. And we've seen that different LLMs, contexts, and edit formats have their own strengths, and if we leverage this diversity, we can increase the success rate. Our model is released both as a NIM and is also available on Hugging Face under the name NV-embed code, and our code will be released very soon.
Yeah, so just quickly wrap up some future directions we're thinking about kind of in general on this coding agent. And I think some points are touched on in prior presentations as well. So far, the focus has been on correctness, right? So Sweetbench is about passing unit tests. But real world is much more than about passing unit tests, and also it's much more about more than Python programming only. So in John's talk, he also already mentioned the Sweetbench multilingual effort, right, to extend to other languages. And there's also a similar effort on the multi-Sweetbench. And the other dimension is the kind of other aspects of evaluation, right? So beyond correctness, so there are performance, you care about how fast your code runs, and the security, you want to write secure code. And also there are some related ones which involve programming such as data sciences. And I think this is the next natural direction to kind of develop things, and there are already works that has been kind of hinting at that direction. And the second is the RL, right? So like that's the next axis of increasing the base model's capability, because a lot of the improvements from Sweetbench is directly benefiting from the base model's ability. And the Deep Suite, that's one example that use RL to improve the end-to-end agent's ability to resolve some of the issue. Right, so like in RL, the most important thing is obviously they have the environment set up, but also the reward. What do you provide? And that kind of ties into my previous slide in terms of saying, okay, like what kind of the objective you want to optimize, right? So there you can define the reward by to kind of inject domain knowledge and to guide the learning process. And finally, the last thing is algorithmic challenges. For example, like open hands, which is another very popular agentic scaffold, a single trajectory can go up to 100 steps. So it's a very long horizon task, and the long horizon reinforcement learning in general is a very challenging task because you need to have very efficient exploration for the model to try different solutions and then finally get to the right answer. So kind of like there's a lot of challenges in this RL for agent improvement, but I think like that's a natural next step for the next step function in capability increase. And with that, that's all for us, and happy to take any questions. Thanks.
Thanks for the presentation. Good work. For the localization, is this a multi-stage approach where you do some sort of vector search, or does it just single stage where you get the line, like the immediate lines, like top K? How does this exactly work? Or vector plus agentic?
Yeah, thanks for the question. Yeah, so it's a multi-stage. So we have the file localization, which is using embedding model, is kind of like the vector search you mentioned. And that gives us a list of top relevant files. And the second stage is the localization agent that narrows down to specific functions. So that's the next stage.
Okay,
yeah.
Great. So at the second stage, do you guys provide any structural information, like sort of like an AST or like enriched, augmented information? Is it just function boundaries and stuff like that, or just lines?
Yeah, that's a very good question. So that's the repository graph we built. So it is using AST, the abstract syntax tree, to parse our specific entities, and then use LSP to step the connections, like calling connection and the containment connection. So the agent uses as a graph to navigate the code base to do the localization.
One last question quickly. Did you analyze the failure modes in the localization? Do you have any insights into why this multi-stage approach is failing, maybe, for the false negatives or positives? Thank you.
Okay, that's a good question. We didn't do very deep analysis on why, but a lot of is because it's two-stage. If the file localization is inaccurate, for example, the file localization doesn't contain the right file, then kind of the agent is looking at the wrong place to start with. Then it has so that explains a lot of it. I'm sure there are other issues, but we haven't really dived deep into that.
Thank you.
Probably only have time for like one more.